Thanks, Mike, for the kind introduction and for having me here. Um, Today, I would like to talk to you or start with my perspective on what the challenges are. I think which also helps you to see or to helps me to communicate my mindset on this topic. And then I'm going to report a bit about observations that we've made, I've made and colleagues have made on reproducibility in the area of GIScience. And I'll introduce some approaches on how we can improve things. So let's start with the challenges. So the biggest challenge is that we use computers and we use them for everything. And we like to use computers. They make our lives easier, right? So they help us doing things that we couldn't do without them. But using computers also has led to, I would say, some questionable practices and habits that we have. And the problem there is that we sort of have, I sometimes call that virtual laboratories that we have. And they are a mess. So maybe Dawn can raise their hand. So who has ever worked in a wet lab? So chemistry, biology, so a few people. So I've never done that myself, but I imagine that if you do that as an undergraduate, you get told how to behave. Like you wear your lab coat, you wear your goggles, you take notes, and you meticulously write down how you do things so that you can understand what you did a week, a year later. We don't do that with our computers. And it's amazing, it's a wonder of technology that I can close this thing today, open it up tomorrow, and it's all still the same. We don't value that enough. And as researchers that work with computers, we need to pay more attention to our virtual laboratories, how we set them up, how we document our environments there, and to take on reproducibility and replicability. So I want to start with what some people call Clearbout's claim, and that's that an article about computational result is an advertising, not the scholarship. And the actual scholarship is the full software environment, code and data that produce the result. And that's really, I think, one important starting point is the PDF that you download or that you publish is worth nothing without the data and the code. That is, of course, a problem because that's how scholarly publishing works still today. So I think that one observation or one challenge is that all stakeholders in science and in scholarly communication lacks crucial skills and tools to enable this actual scholarship, to disseminate that. And there's a lot of literature on how to do things, and we'll get to that later as well. And then another challenge, so I put this especially as a challenge here. So this is the rainbow of open science practices. So open science has a lot of ideas and approaches for us to work more openly. Often that leads to more reproducibility, but there is like a lot of platforms, tools, these logos that you see on the right-hand side. So I know all of them by now, but as I said before, I think about this every day. And for researchers that actually have to do their own science and research, and that for them it can be overwhelming and hard to find which tool to use here. But if you wonder about open science, this rainbow is a good starting point. So the tools that we use or that we're told to use, they change constantly, and that's a big challenge for researchers that we have to keep up with. And I don't only talk about technical tools, I also talk about concepts or processes like preprints, open notebook science, writing a blog, doing web native production of articles, things like new stuff like overlay journals, if you have heard of those, or altmetrics. So there's a lot of stuff happening around us. Technology is pushing science, and it's hard to keep up with that sometimes. And then when we talk, maybe somebody said, or a few people said, I work on open science, so that's good. So openness is very important. Transparency is very important. but I found this recent article from the domain of high energy physics from CERN, and they said that openness is not enough. So openness is not enough. It's not enough if we have open access to results and open data, but we need to also to worry about processes, and openness cannot be an afterthought, and because then it will never work, and openness in itself does not guarantee reproducibility or reusability. So we really have the big challenges that we have to tackle things from the start. If you do your research and then you want to publish it and your paper gets accepted and you start thinking about reproducibility, then that's way too late. So R&R requires new research practices and constant consideration during my data analysis, my own research, and they come up with a few guiding principles that I can recommend you take a look at. I would also say one challenge is that science is struggling away. So who of you does not know what a p-value is, or has a rough understanding of a p-value? Right? So it's one of the measures that we like to use in science to say if some conclusion that we come to, or the data supports the conclusion that we come to. So this is a fun plot by Jeff Leake, medical, I think he's actually a medical practitioner, but works in the domain of bioinformatics. And he has put up this plot on his blog a while back and asked the question, notice anything funny? So what does he do here? He plots p-values on the horizontal axis, and on the y-axis he has different fields. And what you can see there is that there are these curious spikes. And you cannot see the values here, but you can pretty easily guess what the values are, what the spikes are. There are 0.01 and 0.05, which are the commonly accepted values for statistical significance. And basically the question here is, can it be that this is the actual data that people have in their daily research? And the answer is, of course, not. And the most funny thing is, of course, that in economics, a p-value of 0.05 is apparently not publishable. So, what do I mean with science struggles? We work in a field where there's publication pressure. We need to publish our results to get funding, to get the next job. We have, you could say that the academic award system is broken a bit. That pushes us in this direction. We have the publication bias, for which this is a nice illustration. We have harking, so people maybe not intentionally, but effectively do cheat because they collect data and then they restructure their analysis, or they have come up with a new hypothesis. So harking, if you don't know the term, it stands for hypothesizing after results are known. We have a reproducibility crisis that I'm not sure it is one, or there are different opinions on that, if there really is a crisis, or maybe if it's an opportunity. We have fake journals, or fake journals is actually not a good term. The better term is predatory publishing, right? So we have people taking advantage of the publication pressure. And we have big challenges in science communication. The general public does not always understand what scientists say. And for us in this room, like the big topic like climate change is probably we're not thinking about that in the same way as the general public does. And that's a problem in science communication that is, becomes more and more apparent for more and more scientific fields. Okay, another challenge is that we have different terms that we could use. We already have two in R&R, replicable and reproducible. So for today, or for my talk, I'm going to use these terms a little bit differently. So reproducible for me means that somebody does analysis and provides enough information for somebody else to redo the whole thing and come to the same results. It's a more technical perspective. Replicability is a lot stronger. It means that somebody from the same hypothesis might collect different data, use different methods, but comes to the same conclusions. It's the replication crisis that made bioinformatics and biomedical research push to where they are now, and I think they are easily 10 years ahead of us in terms of replicability and reproducibility. Well, the reason for that is clear. They work on drugs for people, and with the consequences that come with the mistakes they make. And but another term that's more recent, actually from last year, and that tries to break up this problem of what do people mean when they say reproducible and replicable. There is a nice preprint by Barber who analyzes the different schools where this comes from. I think we hear more about that later. And that's pre-producibility. And I like this a lot because this is Philip Stark from the US who said an experimental analysis is pre-producible if it has been described in adequate detail for others to undertake it. Reproducibility is a prerequisite for reproducibility. And what I really like here is that it's more about the mindset and how we do science that stands behind pre-producibility. There's also this nice tweet and quote from this article. It says, science should be show me, not trust me. And it continues, it should be help me if you can, not catch me if you can. Right? We are in a way, we are forced to compete in the scientific setting that we have. But yeah, it should be more about, here is my work. And if an error is in there, let's work together to resolve that error and make an improve, and not about pointing fingers. And I'm not going to talk about replicability today. For me, that really is a lot higher goal, but for me personally, it's 2 steps after reproducibility. If we don't work in transparent and open way, then replicability, I think, is a lot higher standard. It requires changes to the whole funding mechanism because we actually need money to do replication studies. And I think that's more and more years down the line to do that. But I think reproducibility can lead to the situation where we have the resources to do replications. Okay, some observations that we made in our project, Opening Reproducible Research in Münster, during the last years, and also as part of the Agile Reproducibility Initiative. So the first observation that somebody earlier made already is that we are quite lucky because when you type into Google reproducibility crisis there is nothing, no geography, no GIScience. So we seem to be good so far. But we of course have to be careful, but these are the domains that we can learn a lot from. So the first observation that I want to report is a paper by my colleague Markus Konkol with the title Computation Reproducibility in Geoscientific Papers, Insights from a Series of Studies with Geoscientists and a Reproduction Study. So what did he do? He asked geoscience researchers, 150 people in an online survey, in a focus group, in interviews, and to learn about how much they use open and reproducible research and what is keeping them from doing it. One of the results is this list of obstacles for authors and readers. So that's a common distinction that we often make. Am I an author of an article or a reader? And just looking at the top ones for authors, a big challenge is describing the methodology. Another reason for them is losing a competitive advantage, which in my opinion is a perceived, not a real barrier, unless there's more people in this room here who have had an idea stolen from them than not. So if that happened to you, please come to talk to me, because I really need to meet somebody who that has happened to, because I haven't yet. But also technical stuff like prepare the code and data, or that people say they use proprietary software, or they don't think that's relevant yet. And for readers, it's the biggest obstacle is that they're missing the details and the methodology or material to be able to reproduce a work that they read. Another paper by Mark, no, this is another figure from the same paper. So he not only talked to the people, but he also tried to reproduce papers himself, 40 papers. That's a lot of work. And this is just one spotlight on that. So he focused also on the figures, and he was able to reproduce, or he attempted to reproduce 40 papers, which is really not, well, and most of them were not reproducible. And he also observed that there was big differences in the figures that he produced and compared to the figures that were printed or published in the article. And we also in our work focus on figures because they are often used to communicate or to come to the conclusions and to argue or convince the readers that the conclusion is correct. And that's of course bad if we're not able to reproduce the figures. And he has many more of these images. He has not published them yet. Well, he will never publish them because we don't want to point fingers here. The 41 papers he attempted to reproduce are 40 of thousands of papers where he did not even try, where there was no mentioning of analysis, no code, no data mentioned. Right. So these 40 are really great papers because he even tried to reproduce them. But what we see here is that the graphics easily differ. So this is supposed to be the one below. I think is at the top is the original, and at the bottom is the reproduced figure. And this is supposed to be the code that the original author used. And of course, and many things can break when you use software. And here we see that the legend is on the right-hand side or at the bottom. The legend units are a bit different. But you see also that actually there's data points here on this map that are not in the original. Right? And it's supposed to be the data that the author used and the same function to create the graphic and the same analysis. So I'm not saying the author intentionally made this, but more probably is that something has changed or something was not documented in the way. So this can happen if you don't take care of your virtual laboratory. So they found a lot of cosmetic differences, like line width, missing legends, or like missing grids on a map, different font. So that of course doesn't matter, but there's also a lot of these differences where you wonder like how can that be, and how might that impact your trust in the analysis. Then we wrote a paper called Reproducible Research and GIScience and Evaluation using Agile conference papers. So more on this process, how we got there later. So we also did a practical evaluation, and we started with coming up with criteria for reproducibility and a test corpus of papers. So the criteria we roughly divided into input data, then we have something about methods with this maybe pre-processing, analysis and processing, about the computational environment, and then about the results. So we did not try to reproduce papers, but we just looked at what information is provided, what is described, and sorted this into these categories. And the papers that we used were the nominees for the best paper awards of 7 or 8 of the last conferences. So we didn't go 20 years back, right? We don't want to. We thought that might skew the results a little bit, but these are supposed to be the most important papers at the conference, and so we thought let's start with those. And of course, there are always variations and shades of gray in reproducibility, right? I'm not saying there's like 100% that you can. Well, I think there's 100% that you can reach, but I would not impose those to others. Anyway, but what we find is that in our assessment, is you could score a certain level of each category, and 3 is the highest level that you can reach, where we would say, yes, this article did everything it could in providing the data, in providing the methods, in describing the results for us to reproduce it. No paper reached 3 in any category. We have a lot of 1s or 0s here. So we all in all reviewed 32 papers, 5 of which were conceptual, and we did not look at them. We have a very, very good established mechanism for reviewing conceptual papers. It's called peer review, so no need to change that. And we sort of had a 4 eyes principle on this, so we just had these 30 papers. I pick one, I award these points, somebody else does the same. If we don't agree, we discuss with the whole group and sort of came to this, this result. And these reproducibility levels are low, and they're also low over time, like there's no trend over the last 10 years or so. And so 19 of 32 papers have level 1, which means it's understandable from the text, but not more. So basically we understand what the author wanted to do or did, but we cannot access the data, we cannot access the code to rerun the analysis. But that also means that if people are able to describe what they did so that we understand it, there's the potential for them to also provide the other resources, right? So there's the advertisement, we found the advertisement, but we did not find the scholarship. Is our own work reproducible? We also asked that ourselves. So can you reproduce this graphic? You can reproduce the graphic. I'm pretty confident. Please try and prove me wrong. But you cannot reproduce our data because the papers that we read are not openly available. So you have to buy them. So we cannot put our PDFs somewhere for you to download them. But you can ask me directly, of course. So that's also just pointing out that we want to be as transparent as possible, but of course there are sometimes restrictions that you cannot really argue with. After we had these results, we also wanted to ask the authors again what they perceived as why didn't they do it. We didn't have too many replies for that. I think 17 authors got back to us, and we just as this is spotlight at that survey is the hindering circumstances for reproducibility, and they could fill those out. And we actually see here that the main reason for most authors that replied were legal restrictions, followed by lack of time and also lack of tools, and for example lack of incentives had also a lot of, like, darker means stronger reason here. So authors are generally aware of these challenges, but it's just not a priority. And I think that's what has to be changed. It has to become a priority for authors to work reproducibly. So, how is spatial data science doing in terms of reproducibility? Just wanted to put out some ideas here for our workshop, but this is really a core question that needs more evaluation. And I think it would be great if out of this group comes another evaluation, another building block towards better understanding of R&R. So GIS and GIScience, I think this is just a few points that come to my mind when people ask me what is spatial about R&R. I think we have at least from my perspective, a long tradition of like geoservices, so that we access map data online and spatial data online, and we process things online. But that of course has also some challenges. We have remote sensing data sets that get larger with Sentinel-1 and 2 missions, right? So it's not that I can do all my analysis on my own laptop anymore, though I would say that in 80% of research in GIScience, geography, geology, that is still the case. And I think that's good, because for those there are pretty straightforward ways to improve reproducibility. GIS is your user interface based a lot, so it's a lot of point and click, which is an issue for reproducibility. Proprietary and open source software is used and widely used in our field. But more and more, I think, also like scripted analyses. For example, R is also a GIS these days. And we also use maps a lot, and maps are really powerful. That's why everybody wants to use them. I think that's sort of also, that was mentioned before, like our methods and tools are picked up by other domains. But maps are also a creative process. So designing a map today often, I don't know, involves some, again, using the mouse and pointing and clicking and making something look nice. That's always a problem for reproducibility. So this is the observations that I wanted to make today. The approaches towards this. How am I actually doing with time? Oh, you don't know what I've planned. I have like 3 hours of slides now. Approaches. So I would say I group this roughly in two areas. One is more technology and infrastructure, and the other one is more organizations and habits. And we're going to start with the technical stuff. So one approach that I would argue to use more is containerization, which means that and that today means mostly that I talk about Docker. So who of you here has used a Docker container? Very good. So there's the technical people again. So containerization, just in a few words, really means the idea comes from shipping containers to have, and shipping containers, you could say, have an outside interface, like a software can have an interface, and that is they are 40 foot long and this wide and this high. And you can put them on a container ship, and you can put it on any container ship, and it'll just carry the container where it has to go. And you don't really care what's happening inside. And that's also the idea of containers in computer science, that we are able to package an application that runs on a server in a way that it can run anywhere, which means, so the reason why Docker is so successful is because they enable, for example, a technology startup to say, oh wait, we have suddenly 10,000 more users in Japan, let's start 15,000 more servers in our East Asia data center, and with a click of a button, and then that all happens. So that's of course not something that we need for reproducibility and replicability, but the mechanisms to package an application with all the dependencies that it has, and basically describe our virtual laboratory in a way that it's portable and well-defined, we can use that. And by that we can use, in case of Docker, we have a recipe for this virtual laboratory, and it's called a Docker file. It describes all the steps that the computer has to go to create this container, to create an image, and then this image I can start and run into a container, and I can actually move this image to another computer. Another meaning that I create an image for my research, I give it to somebody else, they can run this container on their machine, it'll be the same environment that I had. And there's also research going on into preservation of containers, so there's like preservation experts, librarians working on that, and that's good because we don't have to worry about that. And for preservation, the advantage really is everything boils down to one software that has to be maintained in the midterm or the long term, so that people might even be able to reproduce analyses after 10 years, for example. One example where we use containerization is this work with my colleague Christian Knot, where we packaged a GeoBia workflow, so geographic object-based image analysis, a field that normally uses a lot of proprietary software. And he re-implemented an analysis he had, which is quite complex in open source tools. And then I packaged that in a container, and to demonstrate that it's possible to this domain, that you don't really have to use the commercial software, and you can actually package things in a way that others can reproduce it. And in this case, it was a conflict monitoring application where there's an algorithm that looks at remote sensing images and detects burned down huts in a region in Africa. So very complex workflow, and we had to work a lot to make things reproducible, in the sense that using these many different open tools also means that you have to use them in a specific version, for example, and you cannot just use all the latest versions. So the work that proprietary software companies like Esri or Microsoft do in making everything work on your computer is amazing and undervalued, and but it is possible to use all these different open building blocks to connect them for a transparent and reproducible analysis. A further example in the same area where we packaged a geosimulation model, and this is just to give you an idea of how you could use, or how you then as a reader use a container. And it's really not that complicated, because on the command line you can type the Docker commands, and you say, for example, Docker run, and this is the name of the image. And if you have Docker on your computer, you can type this first line of code on your computer now. It'll hopefully not bring down the network, but it'll download all the stuff, and then you can run it will run the analysis, and you can then, with Docker copy command, take out 2 videos of this of your container, and it'll be that video on the right hand side if it's not running anymore. Maybe I can start it again. So no, but you can. This is one of the main outcomes of the analysis, how the analysis is presented, and a reader or a reviewer could do that. Talking about readers and reviewers, maybe one more comment about this. So I spent literally like weeks on making everything reproducible, that you really just had to do one click. And then we submitted this paper to a journal, and we got a review back, and I think we made some adjustments, and then the paper was published. And then when the paper was published, I thought, yes, I was really happy, and I scrolled through, and I clicked on the link to the data set where all the information was for the reproduction, and the link didn't work, because I didn't flip the switch to make it public. So we got our paper accepted, and I think the reviewers trusted us, which is nice, but obviously they didn't look at it, right? Even though that was one of the main selling points of the paper. I hope it's more useful to other readers. But it's really, the question is, how can we make things more accessible also for reviewers and readers alike? One approach to do that is Binder. If you haven't heard about that, it's also based on containers. The idea is that you can publish your code and your data in an open repository for code, for example, GitHub or GitLab. And then you can put that link in here, you click a button, and they will start on some server a virtual environment, your virtual laboratory, for you to access, and also for all the readers to access. So an example for that, and by that, Binder is an enabler for open notebook science. And notebooks are to me, one of the most important approaches that you can take to improve the reproducibility of your research. Here's an example for, let's call it environmental citizen science. So the video on the right-hand side, you actually see an RStudio instance in the browser, or an R development environment in the browser that you can also start when you click on this button, and a browser opens, and you have this RStudio version, and you can look at the analysis, you can see the code on the one side, you can rerun things interactively, and that is what Binder does for us. And at the moment, it's all for free. And the idea that's behind this is, or the abstract idea behind this, is literate programming. term introduced by Gentleman and Temple Lang a while back. And the idea there is that code and text are intermingled, mixed in one document, and this document is text-based. So librarians like that, and it means that we can, look at this text with a computer, and it can produce different outputs. One output is in the editor that I can change the document, but also another output is, a PDF or an HTML file with interactive graphics, for example. And the great thing is that I just learned last week is that Esri has a public notebook server online. I think that's under-advertised, but I think that's an amazing step. So one of the main notebook tools out there is called Jupyter. It comes from the Python domain. Data science is a lot used in the data science domain, and you can go to notebooks.esri.com and look at some example analysis, and I think that's the best way to understand the power of notebooks. Another example or approach that's taken I want to mention is CodeOcean, which is a cloud-based computational reproducibility platform. So they developed a reproducibility platform that's, for example, used now or together with the Nature publishing group for certain journals there. They have the concept of capsules, which really is something like a container, and where if you submit a research paper there, you can create such a capsule and enhance your article with that. I think it's great that this is still one of the leading journals in science. That they go into this direction. I would not personally be happy with the fact that it's a proprietary and sign-up only software, though. Because I think that we as researchers really need to understand the infrastructures that we use and also stay in control of these infrastructures. Another approach to more reproducibility and openness is the OpenEO API. So who here has used Google Earth Engine before? Yeah, so quite a few. That's also not just the technical corner, very good. So Google Earth Engine is successful because they really made remote sensing data analysis easy, right? And also with big data sets. But again, it's a sort of a closed tool. I cannot take my Google Earth Engine configuration, go somewhere else and see if I have the same result. If I work at an institute that does not have access to this specific tool, I cannot reproduce things. I cannot understand things. So OpenEO is a project that tries to solve that. If you are familiar with the open source tool GDAL, it's basically like GDAL for online services. So there's different clients that develop and different backends that are developed. One of them is Google Earth Engine, so they're collaborating with them. Another one is GraphGIS, for example, and you can define your complex analysis they call it like a process graph, I think, and you can hand over this analysis through an online API to different services and run your analysis. And you have no vendor lock-in here, and you can increase the transparency or the reproducibility of your work, even though it requires resources that are not easily configured, like high-performance computing or stuff like that. You can describe what you want to do and go to different services to execute the analysis. And there's a bunch of other packaging solutions that are all more or less working, or some of them are also working with containers that I just want to put here, mention here, if you look at those maybe later. But there's many different tools out there that you can use, especially for different programming languages. But one more higher level concept here, and I think is a very useful approach for R&R, is the idea of a research compendium. So also introduced by Gentleman and Temple Lang. And he uses here the term container, and he doesn't mean the Docker container. There's a generic container. And the term of compendium for the different elements that make up the document and its computations, so text, code, and data, and a means for distributing and managing and updating this collection of things. So a more broader definition we've put on researchcompendium.science. So if you want to learn more about research compendia, you can go there. There's a lot of papers and resources linked there. A research compendium accompanies, enhances, or ultimately is itself a scientific publication, providing data, code, and documentation for reproducing a scientific workflow. So why do I tell you about research compendia? Well, in our project Opening Reproducible Research, we've come up with the executable research compendium. So we wanted not only to have data and code and text there, which could be the actual paper, but also entry points for readers to interact with the packaged analysis. And we want to include the virtual laboratory in the research compendium, meaning that we have a Docker container in this research compendium as an outer container embedded. And if you write a research paper and you create an ERC with our tools, so that our service helps you creating it, we can store that away for you on Zenodo, 5 or 6 gigabytes for the image, a few gigabytes for the data, and things are safely stored. So the idea is that we have different entry points for inspection and extension of this data so that you can, say, swap out a data file between one compendium and the other, or manipulate one parameter where the author said, I'm just saying that this algorithm should use the value of 10 for this, but a reader might have a different opinion. So we allow people to work on that and change that. So it's a research compendium. Well, if you don't know the IT crowd, the British Comedy Series, this is not a compendium, that's actually the internet. But it really is all about packaging stuff in a way that it's not a black box, as in this image, but it's a white box in the sense that everything is there for others to reproduce and really understand what people are doing. And we also want to do that, so we luckily got just a project extension, which is to be announced in April. But we'll be working more on these executable research compendia, and one thing that we actually want to do is that we want to evaluate with students if actually this has an impact on understanding. And I think there is the potential that research compendia also can play a big role in education. So if we have these research compendia, what can we do? So again, a work by my colleague Markus Konkol, in-depth examination of spatial temporal figures in open reproducible research. We can really transform the way that we interact with papers today, because if there's not just a PDF with an image I can look at, I can do more. And he has this new workflow that's not only about discovery, though that can also be improved when there is everything, right? Imagine you can look for papers that use the same software, or papers that work in the same spatial domain. That all works via text today and not using more complex metadata. So I can inspect, I can look at things more deeply, but I can also manipulate parameters of analysis, and I can also substitute. So one of the biggest, or one of the answers that was mentioned most frequently when he talked with researchers, what do you want to do with a paper? Most of them said, I want to try it with my own data, right? And that's not easily possible today. And here the argument is that with these new steps that you can do in interacting with the publication, you also get a higher understanding. So this is not something that's only technology driven. You can do this with ERC. No, it's driven by what we found researchers really want to do with articles. Another activity that I want to mention is Code Check. That's very recent, where we want to develop a web service that for independent reproductions of computations and put a little badge on things so you can say that somebody else reproduced this. But yeah, that's going to be announced as well soon, I hope. So for me, a question for this workshop is really, how would a geospatial research compendium look like? And if we can agree in a certain direction, or if we can agree on certain terms or aspects that such a compendium in our domain has, I think that would be a big step forward. So enough about technology. What do I mean with organizations and habits? So one important thing is that research today has a lot to do with software, right? The virtual laboratories. There's this research by the SSI in the UK, Software Sustainability Institute, with this always summarized with this nice quote: "It's impossible to conduct research without software," say 7 out of 10 UK researchers. And I don't know what the other 3 are doing. And the NSF, another quote here, also puts a lot of money into research related to, or work related to research software. And there's a lot of organizations coming up that work in the domain of people who work with research software or who develop research software. So the term here is research software engineers. And there's a couple of national organizations coming up there. There is an acknowledgement, and the UK SSI Institute has this nice catchphrase: better software, better research. Right? And that's, I think, one important thing where it's not only about technology, but it's about acknowledging that that is the case and how can we support that as organizations. And that also means that focusing on technology alone is not a solution, but it's also about training and acknowledgement of the work that people, or efforts that people spend on computational stuff. So from the Reproducible Agile paper, we came up with a few suggestions what authors could do. And one of them is to take a carpentry course. Who knows what data carpentry, software carpentry is? Excellent, that's good. So there are organizations out there. We don't have to reinvent that. There's also a geospatial curriculum. But if you have an undergraduate student or a PhD student just starting, send them to the carpentries workshop for them to improve the way that they work with their virtual laboratories. You should use free and open source software. I'm not saying that proprietary software and GIS don't have important applications. I personally just think for research, if I want to communicate how I did something, they're not the right tool. We would encourage authors to find local groups of people who have the same problems and work with them and start local initiatives. If you have an eScience group that with experts working only on this, that's great. But just having a mailing list or channel or wiki where you can talk to others and collect resources is already a big step forward. But the most important thing are that authors have to change their habits, and that's a very hard thing to ask of somebody. So we need to get authors to use electronic lab notebooks and to follow the advice that is all out there. So there's fun papers like Good Enough Practices in Scientific Computing or 5 Selfish Reasons to Work Reproducibly. So the arguments are out there, the resources are all out there, the technical solutions for many, many problems are out there. We just have to nudge people more towards that. But it's not only about the individual authors. So I think a very important idea is that conference and scholarly societies, and that's what we suggested to the Agile group, is that there should be awards for reproducible papers. Right? We need to give R&R a stage so that people are willing to put in the additional efforts, even if it's perceived additional efforts. They have to get something out of it. And we think, for example, in the Agile case, that can work because reviewers already suggest best papers. But it could also be that there is actually a new committee working on the reproducibility aspects, and somebody could be chair, and then you get reputation for that. The idea of badges also taken over from software development, that you get a badge if you do something nice, and that could also be highlight papers that are reproducible And there's research that shows that it works. So there's research showing that journals that introduce open data badges actually after a few years have more data. More open data published. You could have an extra track or submission type specifically targeted at reproducibility aspects. And the most important thing are, in my opinion, are the author guidelines, because it's not only about carrots, we also need to take out a stick. And author guidelines are the one thing where we can tell researchers what to do. And we do need to do that with open educational resources, open material. We need to help them doing something. We need to tell them what repositories to use, for example. But it's not only about giving credit, but also a little bit about telling people what to do. And we are very lucky to be able to do that now for the Agile conference, that we develop new author guidelines. Well, an open access for me today should be a no-brainer. I don't know why anybody would still publish in a non-open access journal. Impact factor. Yeah. It's just, the question is, do you have to break out of that at some point? Yeah. And there's more and more universities who now officially publicly announce that they want to evaluate people and not impact factors. So I think I say that so strictly because I want to get people thinking about it. I also have published in journals where I thought this has have an impact, but I don't have my PhD yet. If you have tenure and you still publish non-open access, give me arguments. I don't know any of them. Okay, so reproducible research at Agile, maybe reporting a bit about what we did or how I came to be here. 3 years ago, I wanted to do a reproducible research workshop at the conference, right? So just first year in my PhD research, I liked this conference and I wanted to organize the workshop, and I had like a program committee lined up of people, like really important people in the field, and said like, yeah, submit your paper and we'll talk about reproducibility, how you made your research reproducible. I thought like, that's an easy gainer, like you already have the paper, you write another short paper about the reproducibility. No brainer for me, and nobody submitted anything. So that was really, I was really sad. But we still had a few registrations. So we met up and we discussed and we introduced a few more people to the ideas of open science, reproducible research. And out of that came the paper that I mentioned before. So with those 6-7 people, we wrote the paper, we took a look, and then we submitted that to the Agile conference and did this evaluation paper. And when you analyze papers of a conference, you of course want to address that community, but our paper was rejected there because, well, one reviewer was positive, wasn't accept, 2 were rejected, two reviewers said reject because of formal reasons. The PDF was too long, because I attached the whole analysis and the workflow. I converted my digital notebook into a PDF, and that didn't go through. So that was really unfortunate. As reviewers, if you are reviewers, I asked you to scroll down to the end of the document and read. Well, but we published in a journal, better impact factor. And then we had a second workshop where we talked more about there were 20 people now, 25 people that we introduced to tools on reproducible research, and the sort of the publicity or the acknowledgement that we got there, and also led to an initiative. So the Agile conference, or the Agile organization, gave us money to meet and to invite experts to develop new author and reviewer guidelines. And this is 3 years after the first workshop, 2.5 years after the first workshop. So I think that's not too bad. And we hope that we can come up with something that's usable. And I think whatever is discussed over this 2 days, I will take with me to our writing of these new guidelines. And hopefully that's useful for other conferences or journals as well. So the goal is the reproducible conference. I'm going to speed up a bit. So journals and publishers basically can do the same thing, and there's interesting activities there also in other domains that we can learn from. One that I can only recommend is eLife, a journal in the biosciences, bioinformatics, life sciences, sorry, that do amazing things towards more reproducible research articles. And also thinking a little bit outside of the box and how we can maybe game the system. One of these examples, or one example that I know of, is the Elsevier journal Information Systems. When you submit a paper there, you might be invited to submit another paper in the reproducibility track that they have. And on this paper, the reviewers are co-authors. Right. So this is a nice trick to acknowledge the efforts that reviewers have to spend to really review computational papers. And so why not make them co-authors on this reproduction effort? Okay, as a summary. So I started with challenges. I say that our digital laboratories are out of control, and there really is sort of disruption happening in scientific publishing. With overlay journals, independent journals, and all these different technologies that drive not only science but general disruption in the society and how we communicate. At the same time, academia is extremely conservative. Right? So our mean to acknowledge people's work is the same as 200 years ago. So how can we nudge scientists to towards more reproducible methods? So I made a few observations. Most research today is not reproducible. Although open science and reproducible research has clear benefits both for communities as for individuals. If your work is reproducible today, you will have a lot easier job in 5 years when the new data set is out to write another paper with the same method. Your future self is your best co-author. So there are these benefits out there, but we have to tell people more about that, and I hope that you find in the resources in my presentation some material for you doing that. But it's really hard because we must leave our comfort zones, and we must change our habits, and as communities we need to provide like a safe harbor to do that. And the notion of pre-producibility, I want to iterate that again, is that we all in this together. Nobody wants to cheat, nobody wants to work irreproducibly normally. Yeah? So if we cut each other some slack and acknowledge that science is hard, that's also a big step forward that we can take as individuals in our daily work with colleagues or as reviewers or as editors. That does not take big organizational change, but small steps that we can take ourselves. So there's some recommendations for what I think you can do, and a lot of papers that you can read if you want to, but for now I want to thank you, and I'm happy to answer questions or participate in the discussion. I hope you agree, and if you're still not totally on board, I look forward to discussing this with you. Thanks.